it back just to check. We don't distribute back, but we just check. 4 times 2 is 8. This is to the power 7. Copy the base, add the exponents. 4 times 3 is 12. Copy the base, add the exponents. And 2x plus 3 to the 5th power. Done. So now we are going to combine these. 4x plus 6 plus 3x minus 12. So this will be x minus 6. All this factor will change. Oh, 7x minus 6. 4x plus 3x, 7x minus 6. So that's why I jump from here, here. That's why I put these circles or triangles, because this part is not needed. I mean, I'm just explaining it. So I have 4x minus 4 to the 7th, 2x plus 3 to the 5th, and 7x minus 6. This is fully simplified and completed. That's how the chain rule works on a problem that it also involves the product rule. So we use the product rule, and for each individual one, when we needed to differentiate it, we had to use the chain rule. Okay, so since I turned off everything and rebooted everything, I no longer have the book in the background, so I have to open it now. Until it opens, I'm going to choose another example for us. Yes, like, let's look at 23. We have f of x equals the 4th root of x squared minus 5x plus 2. This is another example of a non-friendly situation. Not at all. If this were the square root, it would have been much easier. Why? If this is the square root, what do I write? From our previous example, right here. If it's the square root, I write 1 over 2, the square root of this function, times the inner function prime. But that's not the case here. Is there any other way of writing the 4th root? Any other way of writing the 4th root? And we've done that with the exponential rules in chapter R, and we need to know how to do that. It's very important.
1 over 4.
Power 1/4. Excellent.
Yeah.
Very good. So this is x squared minus 5x plus 2, everything to power 1/4. Now, not too difficult, because this is a function raised to a power. How do I differentiate a function raised to a power? Can anyone give us an idea?
Four times whatever is in the parentheses.
Careful.
Minus 1.
1/4, the function to 1/4 minus 1 times the inner function prime. Good, awesome. So 1/4 times this function, 1/4 minus 1 is -3/4 times the inner function prime. Can anyone give us the inner function prime?
2x minus 5.
That's it. And you don't have to do anything else with this. That's good enough. Okay, so let's apply the chain rule in some word problems. Okay, let's look at page 172, if it ever opens for me. We want 172. 172. Okay. So let's start. We can work on as many as you want other problems. Let's start with the total revenue. A total revenue function is given by this, where R of X is the total revenue in thousands of dollars. So I'm going to copy the function. So this is 59 on 172. R of X equals 1,000. The square root of X squared minus 0.1x. 0.1, and I wrote 0.01. Nobody knows why. There is no reason why. Good. So this is in thousands. So R of X in thousands. Good. From the sale of X airplanes, fine. Find the rate at which total revenue, which is this function, total revenue function. I always have to read carefully because it could be the average revenue, which is a different story, right? So it says the total revenue is changing when 20 airplanes have been sold. Okay? So when X equals 20 units. So it's asking us to find the rate of change of the total revenue when such and such 20 are there. Okay, sold. Can anyone tell us what we need to do first?
Do you find the limit first?
No, not the limit.
Not the limit.
You mean
but
R prime.
Yeah,
Indeed.
the prime.
Awesome. So 1,000 is a constant. It will stay outside. Now I have to differentiate the square root of x squared minus 0.1x. How do I do that? The square root of a function. The square root of a function prime. Always write on the side the formulas all the time so you don't have any issues with that. So, any suggestions? Yes, I'm ready.
1/2x squared minus.
It has to be the square root
The square root
of x squared minus 0.1x. Very good. Times the inner function prime.
2x. Oh, 2x minus 0.1.
That's it. So now I can find r prime of 20. I'll simplify it a little bit. So I have 500 in parentheses 2x minus 0.1, everything divided by the square root of x squared minus 0.1x. Let me just write this as x because I didn't plug in yet. I don't want to plug in. I'm not going to plug in that. I just wanted to simplify it first. And now we're going to put in the graphing calculator in a moment. So I'm just going to write r prime of 20. And remember, it's in R is in thousands. So let me share my screen. Okay, sharing my screen. Here it is. Graphing calculator. Okay. So you know me already. I prefer to see the function because who knows, maybe I have to go back and plug in something else. Why not? So I have 500. Because it's a product in the numerator, I will not need to put an extra set of parentheses. Then 2x minus 0.1, close the parenthesis, and divide now by the square root. You know me, I love my parentheses. So x squared minus 0.1x. So I see the function. I get out of there, I can go to second and table, and I plug in my 20. So when I plug in 20, I got 1,000.00. Okay. Okay. So that's times 1,000, and we need to identify the measurement unit. Can anyone tell us the measurement unit for this? Measurement unit. It's a rate of change. Say that again.
What was the word problem?
Yes. So what is the measurement unit?
I was asking, could we see the word problem?
Oh, yeah. Yes, of course. Sorry about that. So what is the measurement unit for R prime of 20?
Is it dollars per airplane?
Absolutely. Or unit. Has to have 2 measurement units. Very good. Awesome. Okay, so let's look at, allow me to just discuss 1.8 and we'll go back and we'll work on more problems from both. In 1.8, which is the last section of this chapter, we are looking at higher.
Professor Lee, we
Yes.
just in the book.
Yes, I'm
Not
sorry.
yet.
Yep, thank you so much. Higher order derivatives. So far we talked about f prime, which is the first derivative, or dy over dx. I should put x in here. But now we want to look at the second derivative. Maybe we want to look at the third derivative, and so on and so forth. What will be the Leibniz notation for these two? And so on and so forth. For this one, the second derivative is written in Leibniz notation in the following way: d2y over dx2, not power 2. d2y over dx2. What does it mean? The second derivative of the function. Same thing for f triple prime. The third derivative, d3y over dx3, not dx cubed. When will I apply something like this? For example, if I have the distance function, what if I want to find the velocity function? How do I find the velocity function? What will that equal to? By definition, the velocity is what? The rate of change of distance with respect to time. Rate of change of distance with respect to WRT, with respect to time. So then what will equal velocity? How do I determine velocity? If I have the distance function, how do I find it? If it's the rate of change of distance with respect to time. How do I find it? It's s prime of t. By definition, if this is the function, this will be the rate of change. And the rate of change is nothing else but velocity. What will be the acceleration?
Is it s double prime?
Excellent. The second derivative of the distance, but also the first derivative of the velocity. So let's look at an example. and see how this works. So page 179. So let's choose a function. We can look at any of these. We'll come back. I just want to directly look at an application of what we just discussed. So let's choose 35, 36, 37, 38. You choose, or I will. Any preference?
37.
37, perfect. 37 on page 179. And we have s of t, t squared minus 1/2 t plus 3. S of t is in meters, and t is in seconds. And it says, find each of the following: velocity, acceleration, and the velocity and acceleration when t is 1. Very good. So first, let's find the velocity, then the acceleration, and then the velocity at 1 and the acceleration at 1. Can anyone tell us what a velocity equals to?
S prime. T.
Very good. S prime of t. Can anyone give us the derivative of this function so I can put it here?
Two t minus 1 over 2.
Very good. Awesome. And if I want to determine v of 1, I have 2 minus 1/2, which is 3/2. What is the measurement unit? This is a rate of change of distance with respect to time. What will be the measurement unit at 1 second? What is the measurement unit here?
Meters per second.
Excellent. Awesome. Good. How do I determine the acceleration? I have the velocity, which is the first derivative. I have to differentiate again, or v prime of t, the same thing. What is the derivative of 2t minus 1/2? And I'll put it here. Very good. And since I cannot plug in anything, it's just 2. What is the measurement unit? Careful. The velocity is the rate of change of distance with respect to time, meters per second. But the acceleration is the rate of change of velocity with respect to time. So what is the measurement unit for 2? When a is 1, when t is 1, a of 1 is 2. What is the measurement unit? And it cannot be meters per second, because that's already for velocity.
Meters per second squared.
Awesome. Meters per second squared. It's this over second. That's why it's meter per second squared. Awesome. Very good. So now let's go back and look at a few examples. You choose anything you want, either d2y over dx2 from 1 through 12, or find the second derivative, or find the second derivative, or so on and so forth. Anything you like to choose from 1 through 34. I couldn't hear you, Test. Say it again.
Say 22.
You said 22? This one? 22 it is. So this is f of x, the cube root of x squared minus 1 to the second power. Good. We have to change this into x squared minus 1 to which power? If we don't remember how to do that, then we are in a little bit of a trouble, because we won't be able to continue. That's why we reviewed the exponential rules in chapter R. So what is the power here for x squared minus 1?
It's 2.
2 over 3.
2 over 3. To the inside, 3 The index is always the denominator. Awesome. And now we are ready to differentiate. Can anyone help with x squared minus 1 to 2/3? We bring down the power. We subtract 1 from the power times the inner function prime times the inner function prime. Can anyone give us the inner function prime?
2x.
2x. Since it's just a product here, I will multiply these two and write 2x over 3. If you want to bring this down, you can, or you just keep it as is. It's fine for now. I would like to choose another, something like, oh, you can choose if you want, something like, so we can differentiate d5, d6. This is another way of writing, it's the same thing. So f with parentheses as the power, we never put parentheses, but if it's parentheses, it means it's the 5th derivative or the 4th derivative. So these are the same notation. d6y over dx6 is the same with f to power 6 in parentheses. So let me write this here. So d2y over dx2, we know it's the second derivative. But after a while, we use this notation, which will be d5y over dx to the 5th, or dx5. So we don't want to continue with Roman letters, numbers. So at some point in time, after 2, 3, maybe 4, then we can go to this notation. Okay, so that's what it means. So let's choose one. And then I think we'll stop unless you want to look at anything else. So let's choose one. Okay, I'll choose 33. So f of x equals x to -3 plus 2x to 1/3. And they want us to determine the 5th derivative. Okay, so first we have to find the first derivative, and then the second, and then the third, and then so on and so forth. I bring down the power, and I subtract 1 from the power. I bring down the power, and I subtract 1 from the power. There are not too many nice problems in this book. They're all ugly like that. Second derivative. Bring down the power, subtract 1 from the power. Bring down the power, subtract 1 from the power. Third. Or you can denote it like this. That's fine too. Same thing. Or you can say d3y over dx3. They're all the same thing. Bring down the power, subtract 1 from the power. Bring down the power, subtract 1 from the power. Ugly, as you see. Not friendly. Okay, the fourth one. And then the 5th. Bring down the power, subtract 1 from the power. Bring down the power. What is this? 81. Subtract 1 from the power. Last one. Bring down the power. I think I'm okay here. Please check my numbers. Subtract 1 from the power. Please check my numbers. Subtract 1 from the power. This is how we determine. Obviously, we don't really need much. I mean, we really don't. We're not using derivatives beyond the third. This is just an exercise. And no, you're not going to have something this on the test because it will take 5 minutes on such a problem or more. But you need to see this because you will be asked the first 1, 2, 3 for sure. Not the 4 and the 5th. That's not really relevant.